Welcome everyone to our final two videos on FM1, so Further Mechanics 1 for Further Maths. We're going to look today at oblique impacts of smooth spheres. So this time we've got two particles colliding with each other, rather than the previous exercises where we're looking at one particle colliding with a fixed surface. So the two examples we're going to look at in this first video are where we don't have things in vector form, and in the next video we'll look at how we deal when things are given in vector form in terms of the unit vectors I and j. So in example number 7, before we actually start the example, I just want to clarify the main points here. It's very similar to what you've learnt in chapter 4. When smooth spheres collide, okay, we have a parallel line of the centres here. So the impact, if you like, again, I keep talking about snooker, but it's a good example, obviously, with an aerial view of what happens. If we hit the cue ball and we're trying to put the blue ball, for example, in the centre pocket, then we're obviously trying to line it up so the impact takes place where parallel to the line of centres will be in the direction of the pocket. And that way that would move on and move in that direction there. So in terms of the mathematics where we have collisions, parallel to the line of centres, we have our 2 points that we looked at in chapter 4, where we have conservation of momentum will be held, and we also can use Newton's law of restitution. And then perpendicular to the line of the centres, we have the case where the velocities will be unchanged. So whatever speed we have going into the collision will be equal to that component after the collision as well. So we'll look at these examples to perhaps explain that in more detail. So in example 7, we have a smooth sphere A of mass 2 kilograms. I'm just putting that information slightly out of the way so it doesn't get in the way of all of our speeds and things in a moment. And we have a small smooth sphere B of 4 kilograms. Okay, what we have is that the first sphere A is moving into the collision with a speed of 6 meters per second. Okay, and that makes an angle of 60 degrees with the line of centres. So what we have here is a speed of 6 meters per second. That's an angle of 60 degrees to the line of centres. And again, the line of centres is where our two centres line up when the collision takes place. So what we have after the event, because B is stationary in this example, we'll look at the second example where they are both moving into the collision. But here we have a number of components. So we don't know exactly what's happening here. And I would just go for example, if we call that X and we call that Y, our two components of the velocity of A after the collision. Don't lose too much sleep. I mean, the fact the kilogram is quite low and that one's quite high, it could possibly bounce back. But don't lose too much sleep about worrying about which way it will go. If I've got X in that direction, then that is the direction I take throughout the question. If X ends up being negative, then we know it's actually bounced back the other way. So again, just set those, and then if something is in the wrong direction, you will get a negative answer. So nothing to worry about there. And then B, the understanding is if that was stationary and it is hit in this direction, then we know that there will be, that's supposed to be a horizontal line, my apologies there. Let's call that W, for example. Then B, after the event, once it's collided, it will be moving in parallel to the line of centres there. There will be no vertical component because it was stationary before the collision. So they're the three things we need to know. And as we've set up here, there are 3 unknowns and we've got 3 equations. So we know we can solve everything that we need. So let's go back to our black pen. We'll start with perpendicular to the line of centres because this is the easiest part. So we have for A, okay, we've got 6 sine 60. So that's the speed going into the collision is going to equal y. So that's just going to equal 6 root 3 over 2, so 3 root 3. Now, parallel to the line of centres, we have 2 things to consider. So conservation of momentum, and I'm going to state which direction I'm taking as positive, as you would have done in chapter 4 and chapter 1 for that matter. So before the collision, we have A is moving parallel to the line of centres there with a speed of 6 cos 60. So mass times the speed or velocity is 6 cos 60. I'll put plus 0 in there because obviously before the collision B was not moving. And that's going to equal the momentum after the collision. So we've got 2 lots of x plus 4 lots of w. Now we need our other equation. So the coefficient of restitution, we have the E. Now in this question, I should have put in the middle there. That's where I tend to put it to remind myself. The coefficient of restitution between the spheres is 1/4. So we've got 1/4 equals the speed of rebound. So the speed of rebound is going to be w take away x because of the direction I've taken x to be. So the speed of separation is going to be w take away x divided by the speed of approach, which is 6 cos 60. And if we simplify that, that's going to be 3. So 3/4 equals w minus x. So we've got 2 equations to solve simultaneously. It's easy to make w the subject. So I personally, you can do this any way you like, of course. So w is going to equal 3/4 plus x. So if I then substitute that value to replace w here, and simplifying cos 60 to be a half, so that means we've got that 6 is going to equal 2x plus 4 lots of w, which is 3/4 plus x. 4 times 3/4 is just 3, so 6 take away 3 gives me 3 equals 2x plus 4x, which is 6x, so x equals 1/2. And therefore we can say that w is 3/4 plus 1/2, which is going to equal 5/4. Now the question actually asks us to find the magnitudes and directions of the velocities A and B. So perhaps if I just bring down what's happening with A after the event, just to remind ourselves. So we've got x is 1/2 and y was 3√3. So we can find the velocity of A, and B is obviously going to be much simpler, and we'll come to that in a moment. Now it wants to find the direction, it's asking for the velocity, so we need the speed and the direction. So if we call that alpha, so I've got tan alpha is going to equal 3√3 divided by 1/2, and that gives us a value of alpha which is 84.5 degrees to 3 significant figures. And the velocity of A, so the speed I should say, is going to equal the square root of 3√3 squared plus 1/2 squared. And that is going to equal the square root of 109 divided by 4. I've actually left the answer like that. Or you could write it to 3 significant figures if you wish. Okay, so it's travelling at that speed. So A is travelling with a speed of root 109 over 4 in the direction of 84.5 degrees above the line of centres. And as I said, B is much simpler. We already have an answer for B because there's only the one dimension to it. So B is travelling with a speed of 5/4 meters per second. Should put the units there as well, really. Okay, along the line of centres. Let's move that up slightly for that last point there. So as you can see, there's nothing new to learn. It's just the understanding that when you have two spheres colliding, the collision takes place parallel to the line of centres. So that's where we use what we learnt in chapters 1 and 4. So we use the conservation of momentum before and after the collision in that direction, and using the coefficient of restitution. And then perpendicular to the line of centres, you can see that any speed going in will equal the speed in that component after the collision too. So one more example here. The difference here is that we have both particles moving before the collision. So on example 8, straight away we have sphere A of 1 kilogram and sphere B of 2 kilograms. And this time we are told that before the collision, A is moving with a speed of 4 meters per second at an angle of 45 degrees to the horizontal, and B is moving with a speed of 3 meters per second at an angle of 60 degrees to the horizontal. So if we put the components of the initial speeds in, so parallel to the line of centres and perpendicular, we have going in there 4 cos 45 and 4 sin 45, and here we would have 3 cos 60 and 3 sin 60. So what I'm going to do is just put the 4 components that we can have after the collision. So if I call that A, B, C and D, again I'm not worrying about considering the direction of A and C at this point. If they come out as negative, then we know it's actually going in the other direction. What we have, first of all, let's do the easy bit first again. So perpendicular for A, first of all, we have that B must equal 4 sin 45. Obviously when it's 45 degrees it doesn't matter too much, but we'll just get used to obviously doing our resolving as we would if the angle wasn't 45 degrees. So B is going to equal 4 sin 45 degrees, and for particle B we have that D is going to equal 3 sin 60 degrees. And then if we look parallel to the centres, if we do conservation of momentum first of all, stating which direction we're taking as positive. So particle A was moving in with a speed of 4 cos 45 degrees and the mass was 1. So that's the momentum of A plus B. Now, if I've taken that direction as positive, B is travelling in the other direction, so that is going to be minus 2 lots of 3 cos 60 degrees. So that's the total momentum before the collision, and that is going to equal, I'm just running out of space so I'll just start a new line, the total momentum after the collision. The way I have set them up, I've got them both A and C going in that direction, so I've just got 1A plus 2 lots of C. And then if we do our coefficient of restitution, I didn't write that down again for this question, so we're told that the coefficient of restitution between the two spheres is 3/4. So we've got 3/4 equals the speed of approach. Now they're going against each other, so if you remember that's when we add the speeds together. So the speed of approach is going to be 4 cos 45 degrees plus 3 cos 60 degrees divided by the speed of approach. Got those the wrong way round, sorry. So the speed of separation divided by the speed of approach. So I should have there, if I just quickly squeeze that in at the top. So the speed of separation is going to be C minus A divided by the speed of approach, which is where we add the two things together. Apologies for that. So if I do 3/4 times by all of that, we are going to get that 3/4, 0.75 times by what we have on the denominator there is going to be 3.246. I'll do it in a little bit more detail so our final answers are correct, 2 or 3 significant figures, and that is going to equal C minus A. So that's rearranging our coefficient of restitution formula there, and then the conservation of momentum, we've got 2√2 minus cos 60 is a half, so minus 3 is going to equal A plus 2C. So it's quite easy to find out A in both cases. So A is going to equal C minus 3.246. And then if I equate the A's to each other, I've got that 2√2 minus 3 minus 2C, which is what A equals in our second equation, is going to equal C minus 3.246. So if I put those together, I've got 3C is going to equal 2√2 minus 3 plus 3.246, and we end up with C equaling 1.02. So that one has actually bounced back. And then if I substitute in my value for C into there, you can see that A is going to be 1.02 minus 3.246. So A is going to be minus 2.23. Now the first part of this question is asking us to find out the kinetic energy, so we need the speed. So the loss in kinetic energy, I need to find the speeds of both of these first of all. So before I turn the page, I will just quickly sketch what we've got here and then redraw these on the next page. So we've got a little bit more space. So I've drawn A and B in that direction. So they were my two components for A after the collision, and I've got C and D for particle B. Now, as I've said, A is negative, so A is actually bouncing back as well, and obviously C and D both came out as positive. So if I just flick the page and I write those answers down, what we have there is that A has bounced back with a speed of 2.23. So this is after the collision. And it continued with a speed of B there, which is going to be 4 sine 45 degrees. And then for B, again after the collision, we have that C is going to equal 1.02 meters per second, and our value for here of D was equal to 3 sine 60 degrees. So we can actually find the speeds of A and B after the collision. So that's our velocity of A, our velocity of B. So we need to find the speed of A after the collision is going to be the square root of 2.23 squared plus 4 sine 45 squared. As you can see there. So the speed of A after the collision is going to be 3.60 meters per second, and if we find the speed of B, that's going to be the square root of 1.02 squared plus 3 sine 60 squared, and I've worked out that to be, sorry, I've just got my notes on the previous page, and that is going to be 2.79 meters per second. So the kinetic energy before the collision is going to be a half of 1, because that was the mass of the first particle, and that is multiplied by our initial speed, which was 4, plus a half of 2, which is the mass of our second particle, times by 3 squared. So we've got 9 plus a half of 16, which is 8, so that's 17 joules. And then the kinetic energy after the event is going to be a half of 1 times by 3.6 squared plus a half of 2 times by 2.79 squared. And I make that 14.3 joules. So therefore the kinetic energy lost in the collision is going to be 17 take away 14.3, which is going to equal 2.7 joules to two significant figures. And then finally, it asks for the impulse of the collision. So the magnitude of the impulse exerted by A on B. Well, frankly, you can do A on B or B on A, because that is going to be the same, whichever way we look at it, of course, because no, the impulse is exerted by one is going to be equal to the other. So, for example, if I just looked at what happens to A, and we do the impulse, then the direction, obviously when the two particles collide, is going to be in that direction, so we'll take that direction as positive. Okay, so impulse is the change in momentum. Well, the mass of A is going to be 1, and then the final velocity, as we can see there, is 2.23, and then minus the initial, but obviously because that's in another direction, we know that's going to be plus because the actual collision, it's gone that way and bounced back, so we're going to add the velocities together there. So 2.23 plus 4 cos 45, which was the speed in that direction before the collision. And if we work that out, we then get a solution of 5.1 Newton seconds, again to two significant figures. Okay, so I will go through the vectors questions in our next video. So you can get started on exercise 5C and just stop when you get to questions given to you in vector form, and then we can go through obviously those in the second video. So see you again soon.